9.2 is all about properties of chords. Big ideas here, we'll talk about central angle and inscribed angles, and then investigate some of the properties of chords. So get this into your table of contents, and then we'll begin. First, a definition. A central angle is an angle whose vertex is at the center of the circle. On the left-hand side, we see some examples of central angles. On the right-hand side, we see some examples that are not central angles. Next, an inscribed angle. An inscribed angle is an angle that has its vertex on the circle and sides contained in chords. So here is an example of an inscribed angle, angle ABC. So we see that the arc, ADC, is intersected by the inscribed angle. Here we have some more examples. We've got ABC, BCD, and CDE are all inscribed angles. And then on the right-hand side, you'll see some examples that aren't. Push pause and convince yourself why they are not inscribed. The vertex ought to be on the circle. So some more vocabulary. In this thing, we have the central angle. We could say ABD, DBC are all examples of central angles. An arc is just a piece of a circle. We have different types of arcs. We could talk about minor arcs. For example, arc AC. Then major arcs are arcs that are bigger than 180. So we could say arc DFE, for example. And then a semicircle measures exactly half a circle. So 180, JML would be an example, or up top we have JKL. So here's an example for you. I'd like to sketch this in your notes. If I asked you for the arc measure, the measure of an arc is equal to its central angle. So if I asked you for the measure of arc AB, I see that the 90-degree symbol in the middle for its central angle means that the measure of arc AB is 90. And then what about measure of arc CD? Well, we've got this linear pair situation, 150 and something, so it would have to be 30 to make a supplementary pair. And so the measure of arc CD is 30 degrees. Give a few tries on your own. Measure of arc CDA. CDA is a semicircle, so it has to be 180 degrees. And then CAD. So start at C, head in the direction of A, end up at D. So it's nearly the full circle. It's 330 degrees worth of the circle. So that's arc measure. Arc length is a little bit different. Arc length is the actual length along the perimeter of the circle. Arc length is central angle over 360 times circumference. In order to know circumference, we need a radius. So let's say that the radius is 6. So the length AB would be 90 over 360 times the circumference. Circumference is 12 pi. And so we have 1/4 of 12 pi. So 3 pi would be an exact answer for the length of arc AB. Length of CD is exactly pi units. The length of arc CDA is half of the circle, 180 over 360 times 12 pi. And the length of arc CAD is, again, the reduced fraction times 12 pi gives you 11 pi units. So a few conjectures come next. The chord arcs conjecture states that if I have one circle or congruent circles, two minor arcs are congruent if their corresponding chords are congruent. So let's build a picture of what that looks like. It says two minor arcs are congruent, let's say A, B, and C, D, only if their corresponding chords are congruent. So that means that if the chords the length from A to B is equal to the length from C to D. That allows us to say that those two arcs are congruent. A related conjecture is called the chord central angles conjecture. It says if two chords are congruent, then the two central angles that created them are also congruent. So those central angles would be congruent as well. Next conjecture is called the perpendicular to a chord conjecture. In a circle, if a diameter or a radius is perpendicular to a chord, then it bisects the chord and the arc. So let's draw what we mean. We've got a diameter and a chord, and if the diameter and chord are perpendicular, then the chord is bisected and the arc is also bisected. Next, the chord distance to center conjecture. This one states in a circle or two circles, two chords are congruent if they are equidistant from the circle's center. So let's talk about that. We've got a circle with two chords, and those chords are equal in length when or if the distance from the center to the chord is equal to the center to the chord. So those distances are equal, therefore the chords are equal. Let's work an example problem now. Take a minute and sketch this into your notes. Label the points accordingly. And let's say that circle W has a radius of 10, WL is perpendicular to HK, and HK is 16 centimeters long. Find JL. Well, we know the radius is 10. We know that the chord and the diameter are perpendicular, and HK is 16. Well, the perpendicular chord idea says that 16 is split into equal parts. And we want to find JL. The key here is to draw in a helpful radius. WK is 10 because it's a radius of the circle. And so if we look at triangle JKW, we have a right triangle. We can solve for the distance JW using the Pythagorean theorem. We know the entire length is 10. If 6 is up top, that means that JL ought to be 4. The next example, it's kind of crummy with the drawing, sorry about that. Let's say that chords EF and GH are equal in distance from the center of the circle. The radius is 15, EF is 24, and we want you to find PR. So let's build some, let's figure out what we know, figure out how to get to what we want. The fact that the chords are equidistant from the center means that first they are perpendicular to the chords and equal in length. Likewise, the chords are bisected. So the fact that EF was 24 means that everything else is 12 apiece. Now the radius is 15, so let's draw in a radius to help us find PR. So in triangle PRH, we know the Pythagorean theorem holds, and so x is 9. And that means PR is 9 units as well.